Chapter 8 is going to be split up into two sections. As you've seen so far, we've talked about sequences and series and how to prove if they converge or diverge. I'm going to start with a sequence. A sequence converges if the limit as n approaches infinity of a sub n is equal to L. So I have an example of two sequences here that I'm going to determine if they converge or not. Converge basically means that a sequence or a list of numbers approach a value like a horizontal asymptote, and it diverges if the limit cannot be found or it approaches infinity. So for the first one, if I take the limit as n approaches infinity of this expression here, negative 1 to the n plus 1, n plus 2 over 3n squared. Notice the leading term on top is n squared and the leading term on bottom is n squared. So this equals 1/3, but because n could be even or odd, it could be either plus or minus, so plus or minus 1/3. Now, technically, a limit can only equal a single number, so what this means is that the limit does not exist because it approaches two different numbers, and therefore, this first sequence diverges. Now, let's take a look at the second sequence here. So in the second sequence, I have 1 minus 2 to the n all over n, and I'm taking the limit as n approaches infinity of 1 minus 2 over n to the n power. Now remember, n's getting larger and larger, but technically this is not equal to 0. It's something real, or over here, it's something a little bit larger than the 0, so we have a number less than 1 as a result. So what we're going to do is we're going to use the L'Hopital's technique we talked about in the last chapter. We're going to take the limit as n approaches infinity, and instead look at the ln version of this, which means I can bring the n in front. And then to make this into a L'Hopital's kind of a situation, we're going to need to create a fraction out of this. So the limit as n approaches infinity, natural log of 1 minus 2 over n all over 1 over n. Because now, as n approaches infinity, I have natural log of 1 in the numerator, which is 0, and 1 over a large number, which is 0. So now I'm going to use L'Hopital's limit as n approaches infinity. The derivative of natural log is 1 over the quantity, and then your chain rule, so it's going to be 2n to the negative 2 over the derivative of the denominator, which is negative n to the negative 2. So the n's to the negative 2's cancel out. As n approaches infinity, 2 over n approaches 0, so we're going to end up with negative 2. Now, keep in mind that this is not what our original problem was. Our original problem was the limit as n approaches infinity of 1 minus 2 over n to the n. So since I got negative 2 from using the ln technique, this is actually going to equal e to the negative 2. But it's still a value, which means that this particular sequence converges. So anytime you want to prove that a sequence converges, all you need to do is prove that the limit exists, and then you're done. All right, for series, we had all our different series tests, and I've listed all 10 here. Now keep in mind that some of them only proved a certain thing. For example, nth term only proves divergence. Telescope was best to use for convergence, if you could figure out that the things canceled out. And then alternating series, same thing, this one only worked for convergence. And then we have integral and alternating series error, which I will also talk about at the end. Now, I want to kind of mix things up, basically talk about patterns that you want to look for as we put this together, and similarities, and when you want to use different tests. So these are all kind of scrambled as a result. So basically, if you see numbers raised to their k value or your n value, whatever you're summing over, you want to think in terms of geometric, because the geometric form was a r to the n. So you want to use your exponent properties here. So this would be k equals 1 to infinity. 5 to the k is fine, and then this will be the same as 7 to the first and 7 to the negative 2k. But I could rewrite that as k equals 1 to infinity, 5 to the k, 7 over 7 to the 2k. And therefore I could write it as k equals 1 to infinity, 7 times 5 over 49 to the k. So looking at my AR to the n, 5 over 49 is less than 1. And technically you should look at the absolute value. So this one converges by geometric series. Now, I could also ask for the sum, so I want to show you how to calculate the sum for this. Don't forget that the formula for the sum of a geometric series, n equals 0 to infinity, a r to the n, is equal to a over 1 minus r. So if I look at the sum of this geometric series, I have k equals 1 to infinity, 7, 5/49 to the k. So my a is 7, my r is 5/49. And so the formula is going to be a, which is 7, over 1 minus 5 over 49. However, notice that this a over 1 minus r formula starts from n equals 0, and I have k equals 1 here. So what I have to do is subtract the value I would get if k equals 0. So if k equals 0, I get 7, and so the final answer is 7 over 1 minus 5 over 49 minus 7. Now, over here on the right, I have something that looks like it's in a kind of geometric form, but it's not a number to the end. So if you have something like an expression to the end, you want to use your root test instead. And the root test says you take the limit as the n approaches infinity of the nth root of this quantity. 5n minus 7 over 3n plus 2 all raised to the n. So technically what you're looking at is you're pretending the inside stuff is like r, and so you're looking at the limit as n approaches infinity of 5n minus 7 over 3n plus 2. Now, that equals 5/3. So you can think of it geometrically and say, okay, if r was equal to 5/3, then that would be greater than 1. And so this one diverges by the root test. Now, for the root test, if it's less than 1, it converges, and if it equals 1, it's inconclusive. All right, something like this, and same thing, I'm going to approach it in two different ways. So the first thing you do is you could say, all right, f of n equals natural log of n over n. Now, if you recall, we said that natural log of n is less than n, so that means the denominator is larger, and therefore I know I'm looking at a decreasing function. So I can use integral test for this. But the first thing you want to tell me is that f of n is positive and continuous and decreasing before we start here. So all of those are true. And now we can go ahead and do our integral test. So the integral test says you take a look at the integral from 1 to infinity of ln of n over n. And if this integral converges, then the series does likewise. If the integral diverges, then the series does also. This is an improper integral, so we're going to have to set it up as the limit as a approaches infinity, the integral from 1 to a, ln of n over n dn, and integrate this out. So the integral of this would be the limit as a approaches infinity, the natural log of the natural log, actually, it is, if you let u equal ln of n, so this will be 1/2 natural log of n quantity squared from 1 to a. Don't forget to make your substitution a separate step before you do the limit. So 1/2 natural log of a squared minus 1/2 natural log of 1, which is 0. So as a gets larger and larger, natural log of a approaches infinity because it's an increasing function. So this equals infinity, which means it diverges by the integral test. So that's one optional way of doing it. Now, a second one is to use this quantity that I wrote here. So one thing you want to remember is that we came up with this inequality. 1 is less than the natural log of n, which is less than n. So here, if I divide everything by n, I'm looking at 1 over n is less than ln of n over n, which is less than n. And we can try to do a direct comparison test. For example, I know this one over here, if I compare to the series n equals 1 to infinity of 1 over n, this diverges by p series. And since I know that 1 over n is less than natural log of n over n, if my series over here on the left diverges, then a series made up of larger terms has to diverge as well, and so this one diverges by comparison test. So the only way you can use a direct comparison test is if you know the inequality and the inequality satisfies the needs for convergence or divergence. Now, since I kind of did an integral test, I wanted to go ahead and do integral error here. So I have the series 1 over 4n squared plus 4n plus 10. I want to know how many terms are needed so that the error in the partial sum is approximately 0.001 less than the infinite sum. So the idea is I want to sum from 3 k equals 3 to n instead of from k equals 3 to infinity. But I want to make sure that the difference between those sums is approximately 0.001 or less. So integral error, what we did was, since this was equal to the interval from 3 to n, and this is the interval from 3 to infinity, then the difference between that would be the interval from n to infinity. So I want my error, which is approximately equal to the interval from n to infinity, of dn over 4n squared plus 4n plus 10. And I need that error to be less than 0.001. Now this isn't a way to calculate the exact error because we don't know what the exact sum is, but it's an approximation using the interval. So same thing, I'm going to go ahead and integrate this improper interval. So we have the limit as a approaches infinity, the integral from capital N to a, dn, I'm going to go ahead and complete the square here. So that would be 2n plus 1 quantity squared plus 9. Need that less than 0.001. Factor out the 9. Limit as a approaches infinity. Let's see, that'll be 1/9. Integral from n to a. dn over 2n plus 1 over 3 squared plus 1 less than 0.001. So we're looking at an arctangent here. So the limit as a approaches infinity, 1/9, 3/2 arctangent of 2n plus 1 over 3 from capital N to a. And I'm pretty sure we're good here. And then if I substitute in my bounds, limit as a approaches infinity, let's see, that's 1/6 arctangent of 2a plus 1 over 3 minus 1/6 arctangent of 2 capital N plus 1 over 3 is less than 0.001. Now, as a gets larger and larger, don't forget that arctangent approaches pi over 2. So what we're looking at here is 1/6 times pi over 2 minus 1/6 arctangent of 2 capital N plus 1 over 3 is less than 0.001. And now you're going to go ahead and solve for capital N. Remember to keep everything exact in your calculators until the very end, so use like second entry, that kind of an idea. I got capital N to be greater than 249.496. So the next integer up would be n is greater than or equal to 250. So that means I need to sum all the way up to 250 to get an error approximately less than 0.001. Now you have to go back to your index. So if I recall, my index here was n equals 3. That's my starting value. Yes, okay. And then up to 250. So if I sum from n equals 3 to 250, I have 248 terms that I need to use to get an error less than 0.001. Now, can't use AST here, error, because it's not an alternating series, so the only error you can use if it's always positive or always negative is your integral error. Now, speaking of AST, this will be an example of when to do AST because you have a -1 to the n sitting there at the top. So the AST conditions were that you take the limit as n approaches infinity of the positive quantity, 1 over 4n squared minus 8n plus 3. And you want to make sure that equals 0, which in this case it does. And then you also want to make sure that it's decreasing. So you want to look at, if you were to substitute in n plus 1 for n plus 1 plus 3, if that's less than 4n squared minus 8n plus 3 all over 1. Okay. So this, you want to make sure that it's true for all the n's defined, in this case starting for n equals 4. You can graph it to see if it's decreasing, find the maximum value and find when it's decreasing. You can solve this, you can take the derivative and make sure it's negative. So I went ahead and graphed it, and this is always true for n greater than a half, which is good because I have n equals 4, so we're all set. So this converges by AST. Now, you can stop there if all I ask for is if it converges. I could also ask if it converges conditionally or absolutely. So to converge conditionally, or absolutely, what we need to do is look at this without the negative 1 to the n. If I look at this without the negative 1 to n, we're going to have n equals 4 to infinity of 1 over 4n squared minus 8n plus 3. So again, I want to do this two different ways so you kind of see the comparison. First of all, I'm going to do this by comparison test. So because I have a leading term of n squared on the bottom, I can compare this to the series n equals 4 to infinity. And as an example, I'm going to do 1 over n squared, which I know converges by p series. So instead of doing a direct comparison, I want to show you a limit comparison. So here I'm going to take the limit as n approaches infinity of one series over the other. You get a value, and if that value is greater than 0 and less than infinity, then you know the two series behave similarly. So then my series here also converges by limit comparison test. If it equals 0 or if it equals infinity, it's inconclusive and you have to use a different test. So consequently, since the original converged by AST and the series converges without the negative 1 to the n, this one converges absolutely. The flip of that, if you take away the negative 1 to the n and it diverges, then it converges conditionally. Now, another way to do this, I wanted to go ahead and show, would be the following. So, or. Right. So my or would be the following. I have the series n equals 4 to infinity, 1 over 4n squared minus 8n plus 3. But notice this factors. So n equals 4 to infinity, 1 over, I believe it factors into 2n minus 3 and 2n plus 1. So another thing you consider doing, since it factors, is partial fractions. Those are clue to use telescoping as a result. So if I do partial fractions here, n equals 4 to infinity, let's say a over 2n minus 3 plus b over 2n minus 1. I need a times 2n minus 1 plus b times 2n minus 3 to equal 1. So substitute in n equals 1/2, and you get b equals negative 1/2. Substitute in n equals 3/2, and you get a equals 1/2. We'll get to that in just a second. Alright, so if I substitute those into my telescope, then I'm going to have the summation n equals 4 to infinity, 1/2 over 2n minus 3 minus 1/2 over 2n minus 1. So now if I substitute in n equals 4, my first term is going to be 1/2 over 5 minus 1/2 over 7. My next term, if I substitute in n equals 5, is going to be 1/2 over 7 minus 1/2 over 9. And the 7s and the 9s will cancel out, so I'm left with 1/10. And so this converges by telescope. And same thing then, it converges absolutely. Okay, so those are the two different ways I wanted to show, one with limit comparison and one with telescoping series. Now, AST error. So again, you can only use AST error if it's an alternating series, if you have that negative 1 to the n with it. And the AST error basically says that the error is defined by the first term that you don't use. So in this one here, I had n equals 4 to infinity, negative 1 to the n, over 4n squared minus 8n plus 3. So if I'm using the first 5 terms to represent the sum, then basically my partial sum would be n equals 4 to n equals 8, 4, 5, 6, 7, 8. And so my error is bounded, is at most equal to the first term that I don't use. So if I go up to 8, the first term I don't use is n equals 9. So it's going to be 1 over 4 times 9 squared minus 8 times 9 plus 3. say instead, I want to figure out how many terms are necessary to generate a specific error. So let's say I want my error to be less than 0.005. Well, remember, my error is represented by the omitted term. So first thing I'm going to do is figure out which term I want to omit. So I'm going to take my series definition of 1 over 4n squared minus an plus 3, set at less than 0.005. Put this into your calculator. You get n is greater than 8.089. Now I need an integer out of this. So n is greater than or equal to 9. So that means I'm going to omit n equals 9 from my series. Well, if I omit n equals 9, then I want to sum from n equals 4 to 8. Oh, that's not right. Okay, so I want to sum from n equals 4 to 8, and again, that would be my 5 terms. And I think I did that correctly. Okay, so I think I've hit almost all the series tests. There were a couple that didn't quite hit, so I wanted to get to them now. So for example, over here, k squared is sine squared of 1 over k. Now, one thing you know is that sine k is always less than or equal to 1. So let's try a couple of things here. So first of all, you know that sine squared of 1 over k is always less than or equal to 1 because sine is never bigger than 1. So we could try a comparison. We could say compare to the series k equals 1 to infinity of k squared, which diverges by nth term test. But if I look at my inequality, I know that k squared sine squared of 1 over k is less than or equal to k squared, because sine squared is less than 1. But again, if the larger series diverges, means it goes to infinity, that doesn't necessarily mean a smaller series converges. It could still actually equal a number. So as a result, you can't do direct comparison because it's inconclusive. So let's try limit comparison test. So limit comparison test is you would take the limit as k approaches infinity of one term, which is going to be k squared, over the other one, k squared sine squared of 1 over k, and see if that is greater than 0 or less than infinity. But again, as k approaches infinity, sine doesn't have a value, so even though the k's cancel out, this does not exist. So it's not a limit comparison test either. What this actually is an nth term test. So we're going to take the limit as k approaches infinity of sine squared of 1 over k all over 1 over k squared. So if you look really closely there, you're going to see our squeeze theorem from a long time ago. We can rewrite this as the limit as x approaches 0 of sine squared x over x squared, which is the limit as x approaches 0 of sine x over x squared, and that equals 1. So this diverges by nth term test. So I think I hit just about all of them, and the only one left is the ratio test. And that's what I'm going to do over here. So from n equals 1 to infinity, your flag for ratios, one of them is going to be factorials, or if you have exponents and polynomials mixed together. So the ratio test was the following. You take the limit as n approaches infinity of your nth term, n plus first term, so n plus 2, over n plus 1 factorial, divided by the nth term. Negative 4 to the n plus 1 over n factorial. And you look at that ratio. So you take the limit as n approaches infinity. If I reduce this, it'll be negative 4 over n plus 1. That equals 0, which is less than 1. So this converges by the ratio test. And again, just to summarize, if it's greater than 1, then it diverges by the ratio test. And if it equals 1, it's inconclusive, and you have to do something else. I guess another place that we saw the nth term test was with our alternating series. So let's say I had a series like n equals 1 to infinity, negative 1 to the n, 5n plus 7 over 4n minus 2. So remember, one of the requirements for alternating series was that you take the limit as n approaches infinity of just the positive part. And in this case, it equals 5/4, which is not 0. But again, that doesn't mean that it diverges, because ASTL is only good for convergence. So now what you have to do is change this to your nth term test. Add your -1 to the n. That means this is plus or minus 5/4, which means it does not exist. And therefore, it diverges by nth term test. All right, I think I hit all 10 series. I talked about sequences. I talked about error. I'm actually going to be around next week in room 205 next door to my classroom, so feel free to come see me if you have any questions.